And hello, my name is Zejia and I'm from Yat-sen University. Today, I'd like to introduce our work, MixPert, optimizing mixed precision floating point emulation on GPU Tensor Cores. This work was done with Aoyuan, Xianwei, and Yutong. Let me begin with some backgrounds. Today's GPUs and many domain-specific accelerators incorporate specialized architectures to accelerate matrix multiply accumulate, also known as MMA. This is an essential operation in many applications, and the NVIDIA's Tensor Core, AMD's Matrix Core, or the Google's TPU already incorporates such hardware to accelerate the matrix multiplication. And specifically, these operations are implemented as the hardware primitives. They issue one instruction on a tile of the matrix and compute the multiplication. So to use this hardware, we need to tile the matrix into fragments, and we load the fragments into the hardware and execute the multiplication of this tile in one instruction. So the Tensor Cores units are trading the precision for the performance, because the lower the precision is, the higher the precision, And from the GPU generations, and from different GPU generations, the low precision performance is also growing rapidly. And for example, the widely used TF32, FP16, BF16, or int-A are supported on the Tensor Core units, and it also dominates in the deep learning applications. However, for many other general purpose, the common GPU applications, the need for the FP32 computation is still needed. However, such arithmetic is not supported in the Tensor Core units yet. And these units only supports the low precision, the mixed precision operations. So to bring the performance benefit of the Tensor Core units to accelerate the FP32 computation, we can emulate it using multiple low precision operations to correct the errors introduced in these low precision computations. For example, if we are to preserve the precision of the FP32 using the BF3016, which is introduced by Google, the BrainFloat 16, we may use 6 operations to emulate the computation from a software approach. However, for example, on the NVIDIA's A100 GPUs, the int8 computation is much more faster than BF16, and if we can use, for example, 9 operations to emulate, we may obtain a higher speedup than using the BF16 to emulate. So previously, much of the emulation techniques are using the half precision types like the BF16, and we are exploring the use of the integer computation to emulate the floating point. And I'll give a concrete example on the previous emulation techniques. For example, to emulate an FP32 using the half precision, also known as the FP16, we may split the original number into 2 half precision numbers, and the first one preserve the higher parts of the mantissa, and the second one preserve the lower part of the mantissa. And because of the limited range and limited precision of the half precision, some of the bits in the range and the precision are discarded. So after splitting the number into 2, we may use the Tensor Core to compute them in these low precision arithmetics. For example, the dark green multiplies by dark purple, and the dark green with light purple, and the light green dark purple. So it's 3 operations. However, to do such emulation, we need to scale and quantize them to the low precision 1. And after the computation, we need to upscale and dequantize the numbers. So we may lose a lot. We may lose the precision in these steps. And also, there are many works using the like TF32 or BF16 for the emulation, and we observed that they degrade the precision like 540 times because of the error introduced in the quantization. So as previously mentioned, the integer components on the tensor core has much more faster performance than the floating point, and if we can control the emulation steps for using the integer for emulation, we may achieve much more faster speed up than the floating point. And the second question is how to control the error when we are using the fixed point for emulation. We need to address 3 questions. We need to represent the floating point values into the fixed, using the fixed point to represent the floating point values, and we need to design a method to emulate the matrix multiplication using the fixed point. And we also need to balance the error and speed of the emulation. So for the representation, we are using 3 integers with the shared exponent bits to represent the floating point. I'll introduce it later. And we are using 6 to 9 emulation steps to correct the errors. Then these steps are tunable parameters. So if the application's error threshold is tolerate for larger errors, we may use less emulation steps, and we design a lightweight tuner to tune the number of emulation steps. So first is the representation. An FP32 number is represented as a sign bit, an exponent bit, and the 23 bits of the mantissa. So we can store the exponent in one integer, and the higher 20 bits of the mantissa into 3 integers, and the last 3 are discarded. So for the multiplication of the scalar values is very straightforward. It's very straightforward. For example, to multiply the x by y, and we may accumulate each the segments. We may multiply each of the segments of the numbers in pairs, and we accumulate them together. Then, because the tensor core units are executing the matrix multiply and accumulation in one step, so we also need to deal with the accumulation in the data representation, because the floating point numbers can have different the exponent bits to represent different range. So we need to shift the smaller ones to align with the bigger numbers. So after the shifting, we can share the same exponent bits of the numbers, and then we can compute the mantissa parts of the multiplication. And after doing it, we shift them back to represent the original FP32 values. So For the applications may have many operators, we design a lightweight tuner to search for the area of different operators. We use a sampled input on the application, and we collect the time and area of the application, and we can adjust the emulation steps of the operators. And we evaluated on the NVIDIA 800 and RTX GPU and used the applications from Rodinia, and then previously works they are from the linear algebra, genomics, and machine learning, and self-built benchmarks. So for a single matrix multiplication operations, we obtain 2.1 speedup and 1.2 speedup on RTX, and we preserve the error in a controlled manner. And for the application, in average, we have the speedup of 1.6 times, and specifically the HPL AI and the Sparkler. The HPL AI uses precision refinement steps, so we may use the less emulation steps to accelerate. And also the Sparkler is a genomics comparison algorithm, and we can also use less precision for the computation. So the tuner detects it and uses less emulation steps to gain higher speedup. So in conclusion, we identified the imbalanced performance and precision trade-off on the previously emulation techniques, and we designed and emulation methods on the integer tensor cores and obtained 1.6 to 2.1 times speedup with controlled error. Thank you.
Okay, thanks. I think we are running out of time on this one, so we have time for just one question. If there is, or we can go to the next talk.
Okay, thank you.
Thank you.